So what are we looking at? We're looking at non-parametric tests. When do we use non-parametric tests? When the assumptions of our classic ANOVA model and t-test are no longer valid. It's a peculiar thing to the natural sciences, which is my particular perspective that I'm giving you here in the course. Why is it the case here? Is because often it's really quite hard to get data. We're budget constrained. Some of the sites that we want to look at are far away. We need to spend weeks out in the field. It's just not possible to get the data. We also classify things differently where it's not clear what the measurements mean. So it might not be a clear relationship. We just have an ordering that A is better than B, B is better than C, and so on. But we don't have a numerical number to compare. We just can rank, we have some ranks that we can look at. A is better than B, but we don't have a number that we can look at. And when we have any of these sort of scenarios, it's when non-parametric methods come to the fore. These work for small samples. So there are some alternative approaches called bootstrapping. My view is that those philosophies don't work so well when you have a very small data set, which is the particular case of the natural sciences. So while some people will say, look, there's no longer a role for non-parametric tests, I firmly think that there is a role for non-parametric tests in the specific case of the natural sciences. What do we need to know? Okay, conceptually, parametric methods, these are the ones where we can appeal to the central limit theorem or normal distribution. And these methods are always best if the assumption holds. So as soon as you've got 30 data points, you want to be out of the non-parametric test world. Okay, if you know from other research that the population is normally distributed, there's no point going down the non-parametric methods route. It's only worthwhile if you have small data sets and if you don't know what the population shape is, or if you're particularly worried about outliers. So outliers can have a really strong influence on parametric tests. But because with non-parametric tests you rank the data, the influence of the outlier is radically diminished. So instead of it, if it's the largest value by 1 unit, it gets a rank order that's the highest value. So you have 10 observations, for example, and the last observation is 20, say, in the order. So it will be ranked number 10. If you have that last observation is 200, its rank order will be 10 as well. So just like the median is not pushed around by an outlier, robust methods or non-parametric methods, because they use the rank order, are also not pushed around by outliers. The two tests that we've seen, Mann-Whitney test and the Wilcoxon test, these are both implemented with the same function in R, the Wilcox.test function. We're comparing the ranks of the data. Okay, different people specify the null differently for these tests. So if you go online, you might see a wide variety of different specifications for the null for these tests. We're going to stick with the most general one. I think that that's safest. So as you become more experienced, you might choose to use more tightly defined or different null and alternative setups for these types of tests. But the way that I'm sort of covering them is to give you sort of a fault-free. You won't go wrong with these tests. You might be able to do better if you can become experienced using these tests, but for the base case, the way that I'm covering them, the nulls that we use are always going to be valid. So our Mann-Whitney test, 2 samples, we want to know, are they different? What do? We rank the data from highest to lowest. If they cluster at one end, if all of one group clusters at one end of the rank order, the other group clusters at the other end of the rank order, that is a sign that there are differences in the groups. We have a formal test that can, a test statistic that can decide, how much clustering at either end of the rank order is required to conclude that they're different. You can either calculate large numbers or small numbers. Okay, so what do? We set up a null and an alternative. Group A is the same as Group B. In the example that I gave you, it was Male tuna length is the same as female tuna length. The alternate is just that they're different. Use set alpha just exactly the same way that you've become used to for all of the tests that you've been doing. And then you get R to calculate the critical value for you. So what does it do? Here's my data. I've calculate the rank order of my data. I calculate the rank sum. So I calculate, the sum of the ranks. That's my measure of variation. I then work through the critical formulas, could calculate this test statistic. We don't do that. We just implement it in R. We ask R to give us the test, which it does. And we apply the p-value decision rule. So we just implement the Wilcox-Dot test function in R. We just look at the p-value. It says the p-value is less than 0.05. Therefore, we reject the null that they're the same. Okay, we're just having this very general statement for the null. Same, different. Okay, so we conclude that they're different. All right, so that's the example that we've looked at. So I'm now going to look at another example. So for example, we've been talking in some of the examples about coral reef applications. So these are, very important parts of our ecosystem. We know that there are a number of them around the country, protected or potentially not protected in marine park areas. They perform very important functions. We have two samples and we want to look at them. Okay, so we want to compare two coral reefs. We want to look at the health of them. The particular measure of health that we're looking at is the amount of live coral cover on the reef. This is something that we might be using as part of our environmental management regime. These locations that we need to test could be quite difficult to get to, so we're going to be constrained, we're going to have small samples, and we're going to maybe be a bit worried about the normal distribution assumption because we have small samples. So we want to conduct a Mann-Whitney test, a non-parametric test. So two samples. If we were confident that we could rely on an appeal to either the central limit theorem or that the data was the population was normally distributed, we would just conduct our two-sample t-test. We're a little bit worried that those assumptions won't hold, so we want to conduct a non-parametric test. We set up our sample, we get our sample data. You can see that I've got two groups. I was aiming, I was trying to get 10 samples in each site. Something went wrong. I lost a sample, or something didn't quite work for that sample. So don't have a measurement there. That's what happens. We aim for balance. Often things go wrong. So this kind of scenario, hopefully they don't go too wrong and you don't lose, all your samples, but it's pretty common for things to not work out perfectly. What am I going to do to conduct my investigation? Well, I'm going to create a plot. I'm going to have a formal null and alternate. I'm going to implement the test, and I'm going to look at the p-value to reach a conclusion. And then, of course, I'm going to write up my little research report or my management plan about what's happened to the reef health. So first of all, I have my plot here. So just the same as we would have for our two-sample test, two groups. We want a box plot. I now want to implement my test. So you can see here that I'm going to implement my test. This is my data set. You can see that I've got coral cover here and I've got sites. So these are two columns. So this is what we call long format data. I'm then going to apply my test. So with the Coral AB data set, apply the Wilcox-Dot test function, my response variable cover, and my factor variable site. The sites are A and B. I have 19 observations, two variables. What is my test output? It says p-value of 0.1. Okay, so it says that I have insufficient evidence to reject the null. The null is that the coral cover at the two sites is the same. And you can see I also get all of these warnings. Again, I'm saying to you that the error in the p-value is out here at 3 decimal places, so we don't care. Our practical conclusion is that we have insufficient evidence to reject the null. Now, if you look carefully at that plot, you might get an idea of what was driving that. So you can see while, these bits look a bit different, you can see that there's also a couple of observations sitting up here. So the rank order of the data is capturing those as well. So we're not looking at the shape. Remember, there's no variance ratio test. Because we're looking at the ranks, there's no variance to compare here. It has to be the same. It's the rank order. So we don't have any variance ratio test. That's the world of parametrics. We just look at the rank order of our data. Now, what about if we want to have paired tests? So our paired test is our Wilcoxon test. So we know it implemented exactly the same way. There is a test statistic. We just focus on being able to implement the test in R and read the p-value, which is going to tell us what to conclude. And that's the important thing from a management. We know how the test works. We've seen that, you rank the data, you keep track of the positive differences and the negative differences and so on, calculate your test statistic, all of those things. We've seen that. We only wanted to see that once. We want to get on with, conducting the research. So our setup is going to be that we measure before and after the heat wave at a particular site. So at site A, so I'm going to have measurements before and after. And because it's a paired design, we know that we're going to have matching number of observations. I'm going to be looking at this is the site before the heat wave and this is the site after. So I know that all of these indexing, this is my ID. Okay, I can pair up all of these observations. I'm going to have my testing approach, no different to what we would do for a paired t-test, other than the type of test that we type into R. We're going to have a formal process to follow, create a box plot, which is because it's a single sample or paired, horizontal, null, coral cover is the same before and after, coral cover is not the same before and after, alpha, implement the test, apply the p-value decision rule. So what does our test look like? You can see that most of these guys, there's 0. So even though we're using the rank order of the data, not the actual data itself, most of them are down here below 0. So that's a signal to me that we're likely to have sufficient evidence to reject the null. I'm going to read in my data. So my coral data in here. You can see that I've got before and after. This is my indexing of my observations. How do I implement my test? With my data set, apply the test wilcox.test, before, after, paired equals true. Again, we get all the warnings, which we don't really pay much attention to. It's a shame that they come in bright red, so they catch your attention. And we just look at this value here, which is a p-value of less than 0.05, which means that we have sufficient evidence to reject the null. In practice, we conclude that there has been a deterioration in the environmental conditions at the Coral A site before and after the heat wave event. And that is an opportune time for a break.